Turn on your tap right now. The water that comes out traveled through pipes that average 53 years old. 1/3 of those pipes are over 50 years old. Some are approaching 100. The system breaks 240,000 times per year, once every 2 minutes somewhere in America. Right now, as you're watching this, someone in this country is under a boil water advisory. And in a grid down event, every single electric pump in that system stops. The water doesn't move, the pressure drops, and whatever was in those old pipes, lead, bacteria, sediment, starts moving toward your tap instead. Today I'm going to show you a water system that produces clean, potable water indefinitely from any source. It requires no grid connection, no municipal infrastructure, and it costs $1,200 to build, not $12,000, not $120,000, $1,200. And the reason most people have never heard of it is the same reason you'll understand completely by the end of this video. Here's the number the municipal water industry doesn't put in their annual report. 6 billion gallons. That's how much treated, processed, tested drinking water leaks out of the US pipe network every single day. They built the system to deliver 39 billion gallons per day. They lose 15% of it through cracks in 100-year-old cast iron pipes, and they're billing you for it. The funding gap to fix the system is $625 billion, according to the EPA's own assessment. That number was published in 2023. The fix hasn't started. The municipal water system runs on electric pumps, pressurized pipes, and a chemical treatment process that requires continuous power. Remove the power, and the whole system degrades within hours. That's the infrastructure reality. Here's the business reality. The bottled water industry is a $200+ billion global market that profits from your distrust of municipal water. It replaced a self-sufficient behavior, collecting and filtering water, with a commercial one. The municipal water industry profits from rate monopolies. They have no incentive to tell you their infrastructure is failing. And they have no incentive to tell you that you could opt out for $1,200. I went through the American Society of Civil Engineers infrastructure report card. The EPA's drinking water infrastructure needs survey. Utah State University's comprehensive water main break study covering 400,000 miles of pipe, and the peer-reviewed engineering literature on gravity-fed filtration. The numbers I'm about to give you are not mine. They're from the agencies responsible for keeping the system running and failing to. The system I'm going to walk you through has 4 components. Each one addresses a specific failure mode in the municipal infrastructure. Each is either centuries old in principle, already military proven, or used by hundreds of millions of people globally without electricity. None of it is novel. All of it has been commercially suppressed by the easier option of paying a monthly rate. Here's what you can do with $1,200 while you wait for them to figure it out. Component 1. The source layer. 1 inch of rain falling on a 1,000 square foot roof produces 620 gallons of water. The average American home has 1,500 square feet of roof. 1 inch of rain, a light shower, yields 930 gallons. The US receives an average of 30 inches of rainfall per year in even the driest contiguous states. The math produces more water than most families use. The only reason it doesn't become your water supply is that you were never shown how to capture it. Most people think rainwater collection is a barrel under a downspout for the garden, a hobby, something that doesn't produce drinking water. That's the comfortable assumption. Here's the reality. Rainwater is the purest water in the hydrological cycle before it touches anything. It contains no lead, no chlorine byproducts, no agricultural runoff, no pharmaceutical residue. It arrives at your roof before it has contacted any infrastructure. The contamination happens after it lands, on your roof, in your gutters, in poorly maintained tanks. The collection and first flush system removes those contaminants. What remains is cleaner at source than most municipal supply. Here's the mechanism. The first 10 to 25 gallons from any roof surface after a rain event carry the bulk of bird feces, dust, pollen, and atmospheric particulate that settled since the last rain. A first flush diverter, a vertical pipe section that fills and holds this initial flow before directing clean water to the tank, costs $30 to $50. It eliminates 80 to 90% of roof contamination at the source. It's a one-time purchase. The tank itself is a 500-gallon opaque HDPE poly tank. I'm $200 to $350 for above-ground installation. Opaque is critical, black or dark green, because UV light penetrates clear tanks and promotes algae growth. The tank must be elevated at least 2 feet above the inlet point of the filtration system to create gravity-fed pressure. 500 gallons represents approximately 25 days of water at 20 gallons per day for 2 adults. The rainfall math works for any location. USGS precipitation data is public. Input your zip code, find your annual average rainfall in inches, multiply by your roof square footage, multiply by 0.623. That number is your annual gallon yield. For a median US home in a median US location, 1,500 square feet times 30 inches times 0.623 equals 28,035 gallons per year. And an average 2-adult household water consumption for drinking and cooking, approximately 5,000 to 7,000 gallons per year. Your roof produces 4 to 5 times more than you need. 21 states have explicit provisions supporting rainwater collection. Colorado was the last Western state to legalize it in 2016. Texas offers a state sales tax exemption on collection equipment. Arizona actively subsidizes it. Tucson provides up to $2,000 in rebates per cistern. Check your state before installation. And here's the business model the industry doesn't want you to see. The bottled water industry produces over 50 billion plastic bottles per year in the US. The average American spends $100 to $300 annually on bottled water. Yes, that market, valued at $90 billion globally in 2023, exists entirely because the industry convinced a consumer culture that tap water is unacceptable and the only alternative is a $2 bottle. The rain that falls on your roof is free. The $30 first flush diverter that makes it clean is a one-time purchase. Component 1 cost, approximately $200. You have a source, 930 gallons from 1 inch of rain. But raw rainwater, even from the cleanest collection setup, is not yet drinking water. It has pollen, atmospheric particulate, and trace biological material. The next layer is the one that has kept people alive for 500 years without a single electrical component. Component 2, the filtration layer. Flint, Michigan, 2014. The Municipal Water Authority switched the source from Lake Huron to the Flint River to save money. They did not treat the new water properly for lead corrosion. Over 18 months, 9,000 children under age 6 were exposed to elevated lead levels. At least 12 people died in a Legionella outbreak linked to the same infrastructure failure. Their water system had no independent filtration layer. The treatment was centralized, fragile, and one decision away from catastrophe. Most people think water filtration is a Brita pitcher, maybe an under-sink filter, something that improves taste. That's not filtration, that's marketing. Here's what real filtration looks like. Industrial water treatment uses 3 to 5 stages of filtration because no single medium removes all contaminants. Sediment filtration removes particles. Activated carbon removes chemicals. These are different physical and chemical removal mechanisms that cannot be replaced by each other. A correct 3-stage filtration stack costs $150 to $180. It removes the contaminants the municipal system either adds or fails to remove. It works with no electricity, and it works forever as long as you replace the media on schedule. Here's the 3-stage stack. Stage 1, a 20-micron polypropylene filter removes sediment, rust, dirt, and sand. Stage 2, a 5-micron polypropylene filter removes finer particles, cysts, and suspended solids. Stage 3, an activated carbon block, rated at 0.5 micron equivalent, removes chlorine, chloramines, volatile organic compounds, trihalomethanes. Those are chlorination byproducts linked to cancer, PFAS, pesticide residue, and odor-causing compounds. 3 stages. Each one handles a different category of contamination. Let me tell you about PFAS specifically, because this is the contamination the municipal system doesn't solve. Per and polyfluoroalkyl substances, synthetic chemicals used in firefighting foam, non-stick coatings, and industrial processes, are detectable in the drinking water of approximately 200 million Americans, according to the Environmental Working Group's analysis of EPA data. PFAS are not removed by standard municipal treatment. A high-quality activated carbon block filter reduces PFAS to below detectable limits. Filter cost, $25 to $40 per replacement. Here's how activated carbon actually works at the molecular level. Activated carbon is created by heating carbonaceous materials, typically coconut shell or coal, to high temperatures in the absence of oxygen, then activating the resulting charcoal with steam or chemicals. This creates a porous material with a surface area of 500 to 1,500 square meters per gram. That's the surface area of a tennis court in a teaspoon of carbon. Contaminants bind to this surface through adsorption, not absorption. It's a physical chemical attraction at the surface, not absorption into the material. The binding is strong enough to remove organic molecules at parts per billion concentration. The economics are straightforward. A 20-micron pre-filter costs $5 to $10 and lasts 3 to 6 months. A 5-micron filter costs $8 to $15. Iron and activated carbon block costs $20 to $35 and lasts 6 to 12 months depending on water quality. Annual filter media cost $50 to $80. That is the total annual operating cost of this layer. Compare that to the average American household water bill, $1,140 per year at $95 per month. The industry's business model is centralized infrastructure. It cannot profit from a $50 per year filter cartridge per household. Open a new tab right now. Go to ewg.org/tapwater. Type in your zip code. Read the list of contaminants detected in your municipal supply, then ask yourself which of those your current filter handles. That's the gap this system closes. Particles are gone, chemicals are gone, the water is physically and chemically clean. But physical and chemical clean is not biologically safe. These viruses, bacteria, and protozoa, Cryptosporidium, Giardia, E. coli, pass through even the finest sediment filter. Component 3 is the reason the system produces potable water, not just filtered water, and it uses 15 watts. Component 3, the purification layer. In 1993, Cryptosporidium parvum entered Milwaukee's municipal water supply through the Howard Avenue Water Treatment Plant, a facility that was fully EPA compliant and using standard chemical disinfection. The outbreak infected 403,000 people and killed at least 69. It was the largest waterborne disease outbreak in U.S. history. The cause: Cryptosporidium is chlorine resistant. Standard chemical treatment does not kill it. UV irradiation kills it at 10 millijoules per square centimeter, a dose easily delivered by any modern UV unit. The outbreak that sickened 1/3 of Milwaukee's population could have been prevented by a $350 device. Most people think UV water purification is for industrial applications, overkill for a home system. That chemical disinfection, bleach, iodine tablets, is sufficient. Here's why that assumption fails for a permanent system. Chemical disinfection has 3 problems. First, it requires chemical restocking, a supply chain dependency. Second, chlorine treatment produces trihalomethanes and haloacetic acids, chlorination byproducts that are themselves regulated carcinogens. You're trading one contamination for another. Third, and this is the one that killed 69 people in Milwaukee, chemical disinfection does not kill Cryptosporidium. UV kills everything. At the correct dose, it inactivates all waterborne pathogens, bacteria, viruses, protozoa, by destroying their DNA. No byproducts, no restocking. 15 watts. Here's how the mechanism works. Ultraviolet light at 254 nanometers, the germicidal wavelength, penetrates the cell wall of microorganisms and disrupts their DNA and RNA structure. This prevents replication. The organism is rendered non-viable. The process requires no chemical addition, produces no harmful byproducts, and works within milliseconds of exposure. The dose required is measured in millijoules per square centimeter. The EPA recommends 40 millijoules per square centimeter for 99.99% inactivation of Cryptosporidium. Modern UV LED units deliver this dose at flow rates of 0.5 to 1.5 gallons per minute. The technology has evolved significantly. Traditional UV systems use mercury vapor lamps with a warm-up period, ballast electronics, and a finite lamp life of 9,000 to 12,000 hours. UV LED systems, from manufacturers like Acuva and Trojan, use semiconductor diodes with instant-on capability, no warm-up, 20,000-plus hour lifespans, and a power draw of 3 to 15 watts versus 25 to 80 watts for traditional systems. The flow sensor in modern UV LED units halts water flow if the UV dose is insufficient. There is no mechanism for under-disinfection. It either works or it stops the water. Here's the solar integration. A 50-watt solar panel, $50 to $80, and a 20-amp-hour 12-volt lithium iron phosphate battery, $80 to $120, power the UV LED unit indefinitely from sunlight. The UV LED draws 3 to 15 watts depending on flow rate. At 15 watts of continuous operation, the 20-amp-hour battery provides over 16 hours of operation without any sunlight. 1 day of adequate solar charging restores full capacity. The power system adds approximately $130 to $200 to the total cost and decouples the purification layer entirely from the grid. And here's the business angle that will make you angry. The bottled water industry specifically markets against municipal water quality. It profits from public distrust of the tap. Nestlé, Danone, and PepsiCo, and by the way, Aquafina is filtered municipal tap water, repackaged, collectively generate over $100 billion annually from a product that can be replaced at source for a one-time $350 capital expenditure. The industry funds lobbying against mandatory contamination disclosure in municipal systems because their market depends on the public not knowing that home filtration and purification solve the same problem for less than $100 a year. Component 3 cost, approximately $500, including the solar power system. Sediment is gone. Chemicals are gone. Pathogens are gone. You have clean, potable water produced from rainfall with no grid connection and no municipal dependency. The system produces it at 0.5 to 1.5 gallons per minute, roughly 30 to 90 gallons per hour, more than enough for 2 adults. But there is one remaining vulnerability. The system produces water on demand. What you don't have yet is pressure, and you don't have a reserve buffer when it isn't raining. Component 4 closes both gaps for under $200. Component 4, the delivery layer. Here's the engineering problem every off-grid water system faces. Water at atmospheric pressure produces 0 pounds per square inch at the tap. A typical shower requires 20 to 80 pounds per square inch. A kitchen faucet requires 30 pounds per square inch minimum. Gravity from a 2-foot elevation produces approximately 0.87 pounds per square inch. You need 34 feet of vertical elevation to produce 15 pounds per square inch from gravity alone. Most properties don't have that. The pressure tank solves this with physics. Most people assume pressurized water systems require a large pump running continuously. Complex, expensive, not practical for off-grid. Here's how it actually works. A pressure tank contains a rubber bladder inside a sealed steel vessel. Water fills the bladder. Air in the outer vessel compresses as the bladder fills. When you open a tap, the compressed air forces water out of the bladder through the pipes at pressure. The pump activates only when pressure drops to the cut-in threshold, typically 30 pounds per square inch, and shuts off when pressure reaches cutout, typically 50 pounds per square inch. The tank maintains water pressure without continuous pump operation. It's stored mechanical energy, released on demand. A 20-gallon pressure tank, $120 to $150, provides a drawdown volume of approximately 4 to 5 gallons between pump cycles. That's enough for a typical shower or cooking session without the pump activating at all. For a 2-adult household, this is appropriate sizing. The pump itself is a 12-volt DC demand pump. The SureFlow 4008 or equivalent runs $60 to $80. It draws 4 to 6 amps at 60 to 80 watts, produces 3.5 gallons per minute at 45 pounds per square inch, as it operates on direct solar or battery power with no inverter required. Life expectancy, 5 to 10 years with standard usage. Replacement cost, $60 to $80. That's a low-tech, long-life component that outlasts anything with planned obsolescence built into it. For extended dry periods, a secondary 50 to 100-gallon buffer tank upstream of the pressure tank provides additional reserve capacity. A float valve automatically stops the pump when levels drop too low. Combined with the primary 500-gallon collection tank, total reserve, 550 to 600 gallons. At 20 gallons per day for 2 adults, that's 27 to 30 days of water independence. Here's the total system math. Collection, 500-gallon tank, $200. Filtration, 3-stage inline, $180. Purification, UV LED plus solar power, $500. Delivery, pressure tank plus pump, $200. Total, $1,130 to $1,180. Odds you under $1,200. Annual operating cost, $50 to $80 in filter media replacements. The system is fully functional from day one of installation. It requires no permits in most jurisdictions for residential use. It requires no licensed contractor. It requires 1 weekend. Component 4 cost, approximately $200. Search USGS precipitation data and your city name. Find your average annual rainfall in inches. Multiply by your roof square footage. Multiply by 0.623. Write that number down. That's how many gallons your collection layer produces per year. If it's more than 5,000, the system covers your drinking and cooking water entirely. Let's step back and look at what we've built. 4 layers: collection, filtration, purification, delivery. Each one addresses a specific failure mode in the municipal system. The collection layer replaces the reservoir and treatment intake, the source that gets contaminated. The filtration layer replaces the treatment plant's sediment and chemical removal, the process that failed in Flint. The purification layer replaces the disinfection stage that failed in Milwaukee, and unlike chlorination, it produces no toxic byproducts. The delivery layer replaces the pump station and pressurized distribution network, the infrastructure that breaks 240,000 times per year. $1,130, 4 components, 0 grid dependency, 0 monthly rate, approximately 1 weekend of installation, and once it's running, the only recurring cost is $50 to $80 per year in filter media. That's less than what most American households spend on bottled water in a month. The system that costs $1,200 to build outlasts any crisis because it doesn't depend on any infrastructure that can fail. The rain falls, the filter passes the water. The UV kills what the filter missed. The pressure tank delivers it to your tap. That's not a prepper system, that's engineering. You now have a complete water system for $1,200 that requires no grid and no municipal infrastructure. Here's the part most channels skip. The system fails if the filter media isn't replaced on schedule. A clogged 20-micron pre-filter stops flow entirely. A depleted carbon block allows chemical contaminants through. An algae bloom in a poorly sealed tank contaminates the source before filtration even begins. The system requires 1 hour per month of inspection and 4 hours per year of maintenance. Most people won't do it consistently, and the ones who don't are worse off than people who stayed on municipal water because they believe they're protected when they're not. Maintenance is not optional. It is the system. Second complication, not all rainwater is the same. In areas with heavy agricultural activity, rainwater can contain elevated atrazine and nitrates from spray drift. Near industrial activity, atmospheric deposition adds heavy metals. The 3-stage filter stack handles most of this, but in specific high-contamination areas, reverse osmosis or additional heavy metal filtration adds $200 to $400 to the build cost. The $1,200 system is the baseline. Know your local air quality before relying on it as your sole source. Third, rainfall variability. In California's Central Valley, extended drought periods of 60 to 90 days occur regularly. A 500-gallon collection tank with a 30-day reserve requires supplemental sourcing during extended dry periods. In regions with regular rainfall, this system is your primary water supply. In arid regions, treat it as a primary system that needs a backup. None of these are reasons not to build the system. They are reasons to build it correctly and maintain it honestly. The $1,200 number is real. The filter replacement schedule is non-negotiable. The rainfall assessment for your specific location takes 10 minutes on the USGS website. These are solvable constraints. A 240,000 breaks per year municipal infrastructure is not. A system that produces potable water from rainfall costs $1,200 to build and $80 a year to operate has existed in principle for decades. The municipal water industry charges $1,140 per year for access to infrastructure that breaks every 2 minutes and delivers water through 9.2 million lead service lines. The business model depends on you not knowing the alternative exists. The mechanism of suppression is not conspiracy. It's not regulation. It's complexity. The system has been fragmented into 4 separate commercial categories: rainwater collection, water filtration, UV purification, pressure systems, each with its own supply chain, its own marketing, and its own expertise silo. Nobody sells it as a complete system because no single vendor owns all 4 components. The integration, the thing that makes it worth $1,200 instead of $50,000, is the knowledge, not the hardware. The pipe in your wall is 53 years old on average. The funding to fix it won't materialize for 20 years, if ever. The boil water advisory is not a crisis warning. It's a product announcement for the bottled water aisle. You have a different option now. Physics doesn't care about your water bill. Rain falls, gravity moves it. Carbon adsorbs chemicals. UV destroys pathogens. Pressure tanks store force. These are not opinions. They are mechanisms that operate independently of infrastructure, independently of budgets, and independently of whether someone in a municipal authority decides to change the source without adjusting the treatment chemistry. The system works because the mechanisms work. Build it, maintain it. The rest takes care of itself. 4 components. Start with 1. The collection tank is the most impactful first step. It doesn't require the other 3 to provide non-potable water for irrigation, toilet flushing, and washing. A 500-gallon tank and a first flush diverter costs $230 installed. Start there. Add the filtration and purification layers when you're ready to drink from it. Build in sequence. By this time next month, you can have the first layer operational.